In my previous video, I showed how some atoms are more electronegative than others and how this leads to polar covalent bonds. We specifically looked at the hydrogen chloride molecule, which consists of a hydrogen atom and a chlorine atom that are bound to each other with a covalent bond. But since the chlorine atom is considerably more electronegative than the hydrogen atom, it pulls the electrons closer to itself than the hydrogen atom does. Because of this, the bond between the hydrogen and the chlorine atom becomes polar, and the electrons spend more time with the chlorine atom than the hydrogen atom. This in turn makes the end where the chlorine atom is more negatively charged, and the end where the hydrogen atom is more positively charged. The molecule gets a negative pole and a positive pole. It becomes a dipole. Let's look at some molecules and discuss why they are dipoles, or not. Let's start with methane CH4, which is not a dipole. To understand why it isn't, we must examine the methane molecule's three-dimensional structure. And to do this, we first need to find its Lewis structure. We start here by drawing a carbon atom. Carbon has 4 valence electrons, and I draw them here. To reach noble gas structure, the carbon atom needs to borrow another 4 electrons. A hydrogen atom has 1 valence electron, so 4 hydrogen atoms may bind to the carbon atom in this way. The carbon atom is, so to say, satisfied, because it now has 8 valence electrons. It has reached noble gas structure. And so are the hydrogen atoms, because they all have 2 electrons. We can now see that we have 4 electron pairs, that is 4 electron pair bonds. Each electron pair can be drawn with a line instead, in this way. Now, the electrons, they get along quite well in pairs, but otherwise they want to be as far away from each other as possible. You know, they have the same charge, and because of this, they repel each other, just like the north poles of 2 bar magnets. Since the electron pairs repel each other, they will, when we move up to the third dimension, point into the corners of a tetrahedron, a triangular pyramid, like this. Here we have the carbon atom in the center of the pyramid, and the 4 hydrogen atoms are in the corners of the tetrahedron. In this way, the electron pairs around the carbon atom are as far from each other as possible. Let's write this too, that the electron pairs are as far from each other as possible, and because of this, they point into the corners of a tetrahedron, that is, a triangular pyramid. The methane molecule is not a dipole because there is no part of the molecule which is more negatively charged than any other part. Now, let's look at ammonia, NH3, which is a dipole. To explain why it is, we must once again look at the ammonia molecule's three-dimensional structure. And to do this, we must first check out its Lewis formula. The nitrogen atom has 5 valence electrons, and now I draw them like this. Since it has 5 valence electrons, it needs to borrow another 3 electrons to reach noble gas structure, like from hydrogen atoms like this. Now you can see that the nitrogen atom is satisfied, because it has 8 valence electrons. And the hydrogen atoms are quite happy too, because they each have 2 valence electrons. We can now draw a structural formula for the ammonia molecule, just like we did with the methane molecule. The free, non-binding electron pair we draw with a line up here. Now, what I want you to notice is that in the ammonia molecule there are 4 areas with high electron density, just like there is in the methane molecule. 1 here, 1 here, 1 here, and 1 here. These 4 areas, they repel each other. And what does that mean for the ammonia molecule's three-dimensional structure? Well, as you can see, the molecule's form is a trigonal pyramid, a somewhat flat pyramid with a nitrogen atom at the top. The reason is because the non-binding electron pair also takes up space. If I draw it like this, you can see that the ammonia molecule's 4 areas with high electron density are as far away from each other as possible. But the molecule itself forms a trigonal pyramid. We can write the ammonia molecule's structural formula like this. This black wedge means that the bond, so to speak, points out from the screen, and the dotted wedge means that the bond points instead into the screen. I moved the structural formula to the side a little bit so we can write a few words about this. So, the ammonia molecule is a trigonal pyramid. Nitrogen is more electronegative than hydrogen. Because of this, the bonds between the nitrogen and hydrogen atoms become polar. To make this extra evident, I even turned these bonds into little arrows so you can see extra clearly where the electrons spend most of their time. And since the electrons spend more time with the nitrogen atom up here than with the hydrogen atoms, the nitrogen end becomes more negatively charged. We indicate that by writing delta minus, while the hydrogen end down here becomes more positively charged. We indicate that by writing delta plus. Now, you take that to your notes too, that the nitrogen end is more negatively charged than the hydrogen end. And that's why the ammonia molecule is a dipole. Water, H2O, is also a dipole. Just like before, we must examine the water molecule's three-dimensional structure in order to understand this. And just like before, we start with the water molecule's Lewis structure. The oxygen atom has 6 valence electrons, and because of this, it may bond to 2 hydrogen atoms to reach noble gas structure. The oxygen atom, you can see here, is quite happy because it now has 8 valence electrons, while the hydrogen atoms here each have 2. And just like before, we replace the electron pairs with lines to get the structural formula. We draw the 2 free electron pairs like this. Once again, we can see that we have 4 areas with high electron density, just like in the ammonia and methane molecules. The 4 electron pairs repel each other as much as possible, so when we move up to the 3rd dimension, we can draw the water molecule like this. The 2 yellow balls here represent the 2 free electron pairs. And if we remove them, we see that the water molecule itself becomes bent in this way. We can write the water molecule's structural formula like this. Since the oxygen atom is more electronegative than the hydrogen atoms, the bonds between the oxygen atom and the hydrogen atoms become polar. I draw some arrows here too, to show that the electrons spend more time with the oxygen atom than with the hydrogen atoms. Because of this, the oxygen end of the molecule becomes more negatively charged, and the hydrogen end becomes more positively charged. Let's write that down too. The water molecule is bent. The oxygen atom is more electronegative than the hydrogen, which leads to that the oxygen end becomes more negatively charged than the hydrogen end, and that the water molecule is a dipole. Now let's look at another molecule that is not a dipole, carbon dioxide, CO2. The carbon atom has 4 valence electrons, which I now draw like this. To reach noble gas structure, the carbon atom needs to borrow another 4 electrons, just like before. Just like always, actually. These electrons may be borrowed from 2 oxygen atoms, like this. This is because each oxygen atom has 6 valence electrons, and it can borrow 2 electrons from the carbon atom to reach noble gas structure. Can you see that the carbon atom gets 8 valence electrons? At the same time as the oxygen atoms also get 8 valence electrons. Between the carbon and the 2 oxygen atoms, you can see that double bonds form. This means that we can write the structural formula of carbon dioxide like this. Around the carbon atom, we now only have 2 areas with high electron density. These 2 areas want, so to speak, to be as far away from each other as possible, which means they end up being 180 degrees from each other. Because of this, the CO2 molecule becomes linear. Now, you'll recall that oxygen is more electronegative than carbon. Because of this, the oxygen atoms attract the electrons a little bit more, and the molecule becomes somewhat more negatively charged by the oxygen atoms. The carbon atom is instead somewhat more positively charged. But hold on for a moment here. Didn't I say that the carbon dioxide molecule is not a dipole? I sure did. But look here. One end of the molecule has exactly the same charge as the other end of the molecule, there is no difference between the two ends. The sum of the electric charges coincides with the center of the molecule, which is why the molecule is not a dipole. Let's write that down too. One of the oxygen ends is not more negatively charged than the other one, and that's why the carbon dioxide molecule isn't a dipole. So how can you tell if a molecule is a dipole or not? Actually, there's a method to it called the VCPR method, which I talk about in my next video. But you can summarize it like this. You have to look at the three-dimensional structure of the molecule. To do this, you first draw a Lewis formula and then count the areas with high electron density. When you know how many there are, you place them as far away as possible from each other in 3 dimensions. When there are 4 areas with high electron density, the electron pairs will end up in the corners of a tetrahedron, like, for example, in methane. That's why methane is not a dipole. Likewise, in an ammonia molecule, there are 4 areas with high electron density, but one of them doesn't bind to anything. That's why the ammonia molecule is a dipole. In water, there's also 4 areas with high electron density, but in this molecule there are 2 non-binding electron pairs. That's why the water molecule is bent, and that in turn leads to the water molecule becoming a dipole. The carbon dioxide molecule, however, which is linear, is not a dipole, even if the bonds between the carbon atom and the oxygen atoms are polar. A molecule that is a dipole is always polar. But there are actually molecules that aren't dipoles but still are polar. Let me explain by showing you a molecule that's called ethylene glycol. It isn't necessarily a dipole, but it still is polar. In this model, you can see that the oxygen atoms that are strongly electronegative, they pull equally on the electrons but in opposite directions. This means that actually the ethylene glycol molecule in this configuration is not a dipole, because the sum of the negative and the positive charges coincide exactly with the center of the molecule. But still, the ethylene glycol molecule is polar. Why is this? Let's look at the structural formula here, and you copy it to your notes too. The oxygen atoms here, they are such strong electronegative atoms that around them small local dipoles form. We show that by writing delta plus by the hydrogen atoms and delta minus by the oxygen atoms. Since the oxygen atoms cause a charge displacement within the molecule, it becomes polar. We write that the OH groups make the molecule polar. Also, nitrogen-containing groups, we write them NHX, also make molecules polar. We'll discuss this in more detail when we get to the organic chemistry. Now, here I have a model of a glucose molecule. You don't need to learn its structural formula just yet. You'll have to wait until we reach organic chemistry. But can you still see why the glucose molecule is polar? Well, it's because of the many OH groups here with oxygen and hydrogen. Finally, the molecule that I show here is called hexane. It contains no strongly electronegative atoms at all. No oxygen atoms, no nitrogen atoms, and no fluorine atoms. Only carbon and hydrogen atoms. That's why hexane isn't a dipole at all, but instead completely non-polar. And that's something important to understand when we start to investigate how molecules bind to each other in the following videos.